Hello, and let's talk about the microstrip transmission line. So we're going to be shifting gears a bit. In the previous lectures, we've been focusing on waveguide after waveguide. We did the parallel plate waveguide, we did the rectangular waveguide and the circular waveguide. We could have gone on and done like the coaxial waveguide, and there's a whole bunch of other wacky geometries to look at, like the dielectric waveguide, or the surface waves and those sorts of issues. But we're going to just kind of accept that we've got a basic handle on the fundamental physics of waveguides and some of the mathematical methods involved. And so we're going to take a step back now and look at one of the most popular geometries in, I guess you could say, electrical engineering for just taking signals from A to B. The coaxial cable is very popular and common. So for example, here's a piece of coaxial cable. But another very popular geometry is this, it's called the microstrip line. So I guess you could think of it as microwave strip, microstrip, very funny. And it's basically just a piece of metal, like a base plate, and on top of it is a dielectric lamination. So that's the green void here. It'll have some dielectric constant, epsilon sub r. And then above all of that, there will be a tiny little strip of metal placed on top, and the rest of the void space up here will be space, free space, or air. So you'll have epsilon naught up here, and epsilon sub r down here. Over here, I have drawn a simple cross-section to help you get that idea, where below here, we would say, ideally, it's a perfect electrical conductor. Then you have this dielectric up here, and presumably this geometry may or may not go on forever. In an idealized theoretical sense, we like to think of it as going on forever. But obviously any real system will have to be truncated, so we can at least imagine this as being wide enough such that those edge effects don't matter. And it'll have a height of d here inside that dielectric, which is kind of a shame. I feel like they should have called it h, but oh well, it's d. And then your strip on top will have a width w. And technically you could also say there's a thickness, say t there, but we're not going to get it. We're going to assume it's basically zero thickness. So why is the microstrip so popular? Well, it's because it's dirt cheap. Like here is a plate you can use to make dielectrics or microstrips. And you see how it's just a sheet of copper, and this copper is ridiculously thin, right? If you zoom way in, it's like, a 1/10 of a millimeter thick maybe. And then on top of that is this little thin lamination of a dielectric. In this case, it's called FR4, which is a special insulation material commonly used in printed circuit boards. And then on top, you can just deposit a little strip of copper to create your little top strip here. Okay, and so it's easy to manufacture. You can make this stuff with your bare hands using you can buy this stuff off the shelf, and you have copper tape here to deposit your traces. But more broadly speaking, any printed circuit board is very naturally inclined to this sort of geometry, where I could have a piece of copper on the bottom, a little dielectric layer on top of that, and then I can use photolithography to create various traces to route signals, and I can increase or decrease that width there to change the properties of my transmission line. So let's talk a little bit about some of the basic physics inside of a microstrip transmission line. So to begin, I want you to imagine what would happen if I removed this dielectric entirely. So for example, we look at the cross-section, and I would just see something that looks like this. Okay, so there's my W, there's my D, but I've removed the dielectric, and it's just epsilon naught everywhere and throughout all space here. In this situation, you can see how it's basically a two-conductor transmission line, right? I could hypothetically take a voltage source here and excite each of these conductors with a time-varying signal, and all of the basics of transmission line theory would apply, and we could model it as transmission line, say, with some characteristic Z naught, or characteristic impedance Z naught. So the first question would be, what is the phase velocity of propagation down this system? Well, the obvious answer is if there's perfect electrical conductors and there's no dielectrics anywhere, then we would say the phase velocity is equal to the speed of light. In particular, I like to say c sub 0 to indicate the speed of light in a vacuum. So next, you can imagine what would happen if I immersed this entire system, all of the universe here, with some dielectric. So instead of an epsilon naught up here, I'm going to cross that out and put epsilon sub r. Well, in that case, Maxwell's equations dictate that instead of being the speed of light in a vacuum, it will have to be the speed of light in whatever this dielectric is. So in that case, you'll say Vp is C. So this is why I often use the sub-zero to indicate speed of light in a vacuum. The speed of light here, we could write as, say, C sub R or C sub N for whatever the index of refraction is. But you would define this as C naught divided by the square root of epsilon R, or you could say C naught over the index of refraction for that material, because those are one and the same thing. So that should again be pretty intuitive. If I just fill the entire void with this material, it should slow down the propagation of any electromagnetic waves by this formula. So then the third case is, what happens if I do something in between, where I'm only partially filling the void here with some dielectric, and then I leave the rest of it as free space? Well, we know that the velocity of propagation won't be the speed of light here, and it can't be this one here. It has to be somewhere in between, let's say. So what we would then say is something like my phase velocity. Let's write this out here. I'm gonna call this C sub R here for the velocity of propagation in this dielectric. I'm gonna seize those. That's the speed of light in this material. It'll be less than my actual phase velocity for this situation, which will somewhere then be less than the speed of light in a vacuum. It'll have to fall somewhere in between. So because of that, it's tempting to define sort of an equivalent system. Okay, we can't characterize this thing exactly. The mathematics is just going to be way too hard. But we can at least sort of talk about it in an intuitive sense by defining what is called an effective dielectric constant, epsilon sub E. So let's write that down. An effective, dielectric constant. So it is the equivalent dielectric material such that if I filled this entire void space with that particular dielectric value, then it would yield the same velocity of propagation as this system over here. So we will then say the velocity of propagation for this microstrip line is going to be the speed of light divided by the square root of epsilon sub E. So that the effective dielectric constant is the material such that if I filled the entire universe with this stuff, it would give me the same velocity of propagation as this other material over here. So remember, this is epsilon R for this dielectric. This over here would then be my epsilon sub E. So what we would then say is 1 is less than epsilon sub E, which is going to be less than epsilon sub R. So it's going to land somewhere between that extreme. So the next question is, how do we calculate the effective dielectric constant? Is there any way to model that? Or what about the characteristic impedance of this system here? Like, it looks simple enough, just a few little boundary conditions with some dielectrics here. Can we calculate the electric and magnetic fields around this system exactly? Because if we did know that, we could then use that to calculate the characteristic impedance, or the characteristic capacitance, and the characteristic inductance. Unfortunately, the answer to that is no. There is no simple way to take this geometry, plug it into Maxwell's equations, and get a straightforward solution for these terms, these parameters here. In principle, it can be done, but you'd have to do a lot of boundary condition matching between a lot of Fourier series, and it would just be big and complicated and ugly and horrible. So in principle, this exists if you want to do an analytic closed form solution to this, but in practice, it is just way beyond the scope of this course and even most PhD level mathematicians and physicists. So what we're going to do instead is we're just going to kind of say, well, what if I just do a bunch of experiments and do a kind of approximate curve fit around a bunch of values that I am generally interested in? In that case, the book gives some nice references. In particular, you get the effective dielectric constant is approximately epsilon sub r plus 1 over 2 plus epsilon sub r minus 1 over 2 times this thing over here, 1 plus 12 times d over w, the square root of that, and a 1 over that. Okay, so you get this sort of a thing. So remember, this is an empirically derived formula. Nobody went to the pencil and paper and derived this. This is basically somebody doing a lot of simulations and measurements and coming up with an approximate function to tell you a close enough answer, right? And if you do this, it will not be exact. It will, however, be within, say, 2 to 5% for most geometries you care about, which most of the time is good enough for government work, as the expression goes. So that's why it's this approximation. I've even done some simulation comparisons myself, and these are close, but they don't quite agree with the simulations. But remember, the simulation will take minutes to calculate if you're going over a large number of simulation sweeps, whereas this will be milliseconds to crunch out in something like MATLAB. So the same thing applies for the characteristic impedance. So I'm going to say Z0 is equal to, so this is just in the book, I'm just kind of copying it down. You get 60 divided by the square root of epsilon sub e times the natural log of 8d over w plus w over 4d. And then this big equation here, which is in my notes. So we'll copy it down here again. So just FYI, this is in your book on page 148. You can see these expressions here for yourself. So this one's going to be a little nasty. We're going to get a square root of epsilon sub e times w over d plus 1.393 plus 0.667, so that's probably just 2/3 there, times the natural log of w over d plus 1.444, and then 120 pi over that. So I suspect this 120 pi is actually the intrinsic impedance of free space there. We'll just leave it as that. And this is a piecewise function. So when w over d is less than or equal to 1, you use this expression. And then when w over d is greater than or equal to 1, you use this expression here, and they'll kind of fit into each other nice and neat. So again, this is an empirically derived formula. The book gives some references to how that was done. And you can just take it on faith. This will generally work for most situations well enough. It's not perfect, so you have to keep in the back of your head that if you're using some kind of extreme deviation from some of these simple little geometries, like say if I tripled the thickness of this thing and had a big fat strip, I may go way beyond what this is intended for. But then again, who knows what the bounds are on this, where it works and when it stops working. So that's the thing you have to bear in mind. This is not really an equal, this is an approximation. And I've tested it. It seems to work pretty well for some of the scenarios we care about. And we're going to test this out in our lab when, again, we make some of these transmission lines. So you notice we're just going to lay down some line, we're going to connect it and test it with our nano VNA, and then we're going to apply this expression to see how well it agrees. And what you should find is it'll kind of be in the right ballpark for most of this stuff. Okay. But that's basically most of everything you need to know about the microstrip transmission line. Right? And the book likes to talk about some of the other stuff. For example, if I know, for example, what characteristic impedance I want in dielectric value, I can then solve for my W over D ratio. You could use those big ugly equations. Honestly, it's easier to just graph this thing and do a little bit of curve fitting and do some little inversion that way from the graphs, in my opinion, but the options are there. There's also some issues, of course, with dielectric loss. We'll add some natural attenuation to things. But another important point is that, if we go back here to this geometry, we are looking at kind of the low frequency transmission line equivalent circuit here. Obviously, as I go higher and higher in frequency, there will be higher order modes in this thing, which, as you can imagine, if it was difficult enough just to derive a sort of approximation for the transmission lines, imagine how more infinitely difficult it'll be to do kind of a full field waveguide solution to this thing. So in that sense, just leave that to the PhDs. And honestly, if you're doing 50 terahertz signals in here, you probably shouldn't be using microstrip anyway. So as a simple transmission line, though, this is a great practical system, a great geometry to work with. And these equations give pretty good results most of the time, unless you're going to some extreme outlier situation, right? But that's pretty much all you need to know to work with microstrip transmission line in your upcoming assignments and your labs. And just bear in mind that this is kind of a low frequency-ish. There's a lot of approximations here. It's the low frequency, they says quasi-TEM, so we'll say QTEM, because it's not quite transverse electric, not transverse magnetic. It's not quite transverse electromagnetic either. It's very, very close to that when you get to the lower frequencies or the lower order modes. But as you go higher order modes, you can then imagine, of course, that those blobs of energy will want to start bouncing around in here. And you can even create antennas out of this stuff. So they're called patch antennas. So we're not going to deal with any of that. We're just going to focus strictly on the transmission line aspects of this geometry, just because it's so simple and cheap and practical.